Hello friends, in our previous video we learned how to train a simple neural network. So in this video we are going to learn about RNN. RNN, which represents a recurrent neural network, is a type of network which is designed to handle sequential data such as text, speech, video frames or time series data. So in this neural network you keep on passing the inputs, and based on the input it gets trained and produces an output. Unlike regular feeds networks, RNN has loops that allows it to keep track of past information while processing new inputs, and they are often used in NLP, natural language processing, because of their effectiveness to handle text. So in short, like in simple neural networks, only inputs were passed, right, as the input, but here they have loops. So in multiple hidden layers, each hidden layer is also dependent on the previous hidden layer's output. So input is passed to different hidden layers as well as the output of previous hidden layers, and finally the output comes out. We will look into in details further in the video. So one issue with the vanilla nets is input size is predetermined. Like that these many inputs will be passing in the simple neural network. Right? As in the past video, we calculated the weights and height. Right? Weights and heights were our inputs. So the two inputs were predetermined. It will always handle these type of inputs if it is trained on them. And output size is also predetermined, right? Like you know what output will come, how much amount of output will be generated. But in these kind of neural networks, the output can be multiple, as well as input sequence can also change with time. For example, if you pass a sentence to RNN, sentence can be as much big as it can be, right? Like it can be 5 words, 10 words. So input size can change on the runtime. You can't naturally feed in, say, a sentence with 5 words in one case and 15 words in another case. You cannot do it unless you pad or cut it. This is about the vanilla neural nets, right? Like if you want to feed a sentence to a vanilla neural net, you need to make sure all the sentences are of same amount of words. So in case a sentence is of in case a sentence is lengthy, for example 15 words, you need to cut it or pad it or do some pre-processing on it to make it to an acceptable size and pass it to a vanilla neural network. So that is where RNN comes in. They handle data one step at a time, maintaining a hidden state. This makes them suitable for variable length sequence, both input as well as output. So input as well as output can be variable for them. So there are different types of RNN. Let's look into them one by one. The first one is simple one-to-one, like a neural feed network, one-to-one, where input is fixed and the output is fixed. So here you passed an input, the red color represents the input, the green color represents the RNN, and blue color represents the output here. So you pass the input into the RNN does the pre-processing and gives a specific output. So an example of this could be an image classification, right? You passed an image and it just tells you the label what that image belongs to. Then there are one-to-many. So here you pass a single input into the RNN. There can be different layers of RNN, and each layer will give you one output. For example, in this example, we are passing an input in the first layer of RNN. RNN has 3 layers and they are dependent on the output of previous layers as well, and each layer is producing its own output. So this is like image captioning, like you provide an image but you get a sequence of words. That can be anything, that description of an image or something like that, or the title of the image, but you get a sequence of words, right? So each layer will produce a word. So this kind of RNN is one-to-many RNN. Now there are many-to-one RNN, which is the reverse of the previous one. Here you passed multiple inputs to all the layers of the RNN and you get an output. For example, sentiment analysis, right? You provided a sentence, for example, a good sentence or a bad sentence, and it just gives you if it is a positive or negative sentence, like a review thing. If you want to find out if a review is negative or a positive, this is the example for this. Then there are many-to-many synchronized ones. In many-to-many, you passed some input and you get a multiple output as well. But here the input and the output length is same. For example, let's take an example of a sentence. You pass a sentence and the output will be each word in a sentence, it gets a tag, any tag it could be. So then the number of tags that will be generated will be equal to the number of words that are passed in the sentence, right? So it is synchronized with the input. This is one example for this kind of RNN. Then another is same with unsynchronized behavior. Here the length of input and the length of output can vary. So you pass some words into it, the RNN processes it and it produces some output. Although the length of the output can vary. For example, machine translation. You provide a sentence in English, but you get the output in some other language, for example Hindi or French or something. Here the number of words you will pass in the input may not match with the number of words in the output, right? Because a sentence in different languages can have different length of words in it. So this could be a good example for many-to-many RNN. So let's consider a many-to-many RNN with inputs of x0 to xn that wants to produce the outputs of y0 to yn. Here xi and yi are the vectors and that can have arbitrary dimensions. So they to pass an input into RNN, we convert the words into vectors. We will see in our training example how we do this. But once we train our RNN into the vectors, RNN can use those vectors to produce the outputs. So they work iteratively, updating a hidden state h, which is a vector that can also have arbitrary dimensions. Like it can have multiple dimensions as well. Here vector need not to be of a fixed length like 2 or 3. It can be of any length. So the next hidden state is calculated using the previous hidden state as well as the next input. So as you saw in these diagrams, right, input are being passed to other layers as well, right? So the first hidden state is depending only on the input only, and the next hidden state is depending on the next input as well as the previous hidden state output, and the next hidden state is depending on the next input and the previous state output. So this keeps on going. So if you want to calculate the output of a hidden state, it will be like something like this. So here I'm using a tan-h function as an activation function, and the formula remains same. We have some weights, we have some biases, and we pass the inputs with the weighted sum. We pass the weighted sum of those into the activation function, and finally we get the output. So here wxh is the weight of this input, this red arrow, and xt is our input. whh is the weight of the output that will be passed to the hidden layer, and ht minus 1 is the output of the previous hidden layer, and bh is some constant, it is the bias. So we take the weighted sum of these into an activation function, and we produce an output. The next output, which is the final output, it will be calculated by the same formula, only it is not depending on an input. So we have just a weight and the previous output of the last hidden layer plus a bias. So this is how the RNN works. So which makes it recurrent. So it's a recurrent because the same weights on same input weights, same hidden weights, and output weights as well as the biases are used at every time step. For example, the weight you are using, which is wxh, weight you are using in the first hidden layer, the same weight will be used in the other hidden layer, and so on until unless it reaches the output. So as you saw in the previous video in my vanilla neural network, the weights were different for each neuron, or it could be different on each hidden layers as well, right? But here you just decided on an input weight, a hidden layer weight, and an output layer weight. So input layer weight is responsible for this red link, hidden weight is responsible for these green links, and output weight is responsible for these blue links. And these weights are used again and again for each input as well as hidden layer until unless you get an output. Then after we get an output, we find out what the error is, how much the result differs by the actual output. We find out the error, and based on the error we just shift these weights and train our RNN. We will see in practical how it works. So instead of learning a new set of parameters for each position in the sequence, the RNN shares parameters across time. It makes them efficient and capable of handling variable length sequences. So this is how it looks. Now let's take a problem so that we can train our RNN on that. So the problem I have taken is finding out what language a sentence belongs to. So here, as you can see, this is just a small data set I have taken. So here 2 sentences belongs to English, 2 for Spanish, 2 for French, and 2 for German. So I have just created a huge data set. Let me show you the data set. I will go to the Visual Studio Code and data. So this is the trained data I have generated using ChatGPT. where I have 50 sentences for each languages. 50 belongs to English, German, French, and Spanish. So this is my trained data and this is our test data. After training our model, we will use this test data to test out how it is performing. So let's go back. So each xi will be a vector representing a word from the text. So when we will pass these sentences into our neural network, here we will not pass them as a English word or a normal words that you see in a language. We will just convert them into the vector and we will pass that vector into our neural network, and using that vector the neural network will train and it will understand how to recognize a sentence for different languages. So that is what our pre-processing will be there. So output y will be a vector of containing 4 numbers. So here this is an example of something like this, where we are passing multiple inputs, as we are passing multiple words in it. Each word is a vector, right? So as the length of the sentence increases, the more vectors will be passed into the neural network, right? And the output will be a category, what category the sentence belongs to, right? So this is an example of this type of many-to-one RNN. So output will be a vector itself, as we have 4 categories. It will be a vector of 4 integers, you can say, and the where each numerical value will tell you the probability of the language the sentence could belong to, and the probability that is the highest will be the output. So let's start with the pre-processing. So we will have to do some pre-processing to make it in the usable format, right? So as we know, our data is something like this. So what we are doing first, we are finding how many unique words we have in this whole data set. So for example, hello here is multiple times, right? If I search for hello, it's 2 times here. If I search for this simple word is, it's like 143 times here, right? In other languages as well. Not this, but in the English it is multiple times, right? So we just need to represent them by a single vector. So every time we pass a word into a neural network, if it is the same word, it should look like the same input, right? So we will just find out how many unique words we have in our whole training data set. For that we do something like this. Now after that we create vocabulary of list of all the words that appear at least once in our training data set. Next we will assign an integer index to represent each word in our vocab. So let's look at this in the practical. Let me comment out all this code first. And let's uncomment these 2 lines. So here I'm just looping on my trained data set. I'm splitting them, creating them array, and then I'm just creating a set out of it, because set cannot contain duplicate words, right? So it will just tell us what are the unique words we have. So let's print this as well. Let's leave these 2 sentences for now. Let me run my script. So as you can see, we have 258 unique words that are present in our whole data set. Now let's print these 2 as well. Okay, so now we have created a dictionary of word to IDX as well as IDX to word. In both the cases we have created a dictionary. We have just assigned them a unique index. Basically we just loop through it, and whatever index we found, we just assigned them as a key. And in the word to index as well as index to word, both the manners. So here word to index, if you provide a word, it will just give you an index, what index it belongs to. So the word good is at index 213, and using this, if you provide an index, you will get a word. For example, at 0 we have the word best. After that, now we can represent any given word with this corresponding integer index, right? Because the idea here is, so we have 258 unique words, right? So we will create a vector of 258 in length, and whatever index the word is present, we will just put 1 in this position, and the other position we will keep 0. So this is how we are creating our vector in the pre-processing. So let me show you how the vector looks like. So let me uncomment this much part. So I'm doing something extra as well. Here, if you will see, I'm just finding out how many unique languages we have. So we again loop through our trained data set, which is a dictionary. If I go back to it, it's a dictionary, right? Here a key value pair, and where the value is the language it belongs to, and the key is the main text. So I am just looping through all my training data set and just finding out how many unique values we have, because values are the languages that are present in our data set, right? So we get how many unique languages we have, and this is our output size for our RNN. Then I am just creating a dictionary similar like this for these as well to provide an index to each language. Here I am just creating the vector for each word. For example, let me uncomment it. So this is one of the sentence we are passing, right? So let's comment this print length and let's comment these two printing statements as well. So here we are passing these words and we are creating our inputs, right? Let's see how our inputs will look like. Let me run this. So this is how our vectors are looking, right? So we pass two words, right? Which is good as well as was. And then we know that good belongs to the index of 213, right? So you can see all of them are 0, but at this place we have 1. This is the index, the word is present in the dictionary, the one we have created here. So at that place we will put 1 and all the other places will put 0, and it's a vector of 258 and 9th. So this is now another vector we have for was, which is this word. So here again we will have 1 at one of the unique place. Let's look for it. Let me search for, here it is. So here we have 1 and all the other places are filled with 0. So this is the vector that is representing the unique word was. This is how we are creating our inputs, which will be passed into the RNN, and RNN will get trained on them. So let's move forward. Now we will start by initializing 3 weights and 2 biases of our RNN. 3 weights obviously, 1 for input weight, 1 for hidden layer weight, and 1 weight for output layer. Now we will use this random function and NumPy which to initialize our weights as well as biases. So this is the feed forward layer. So if you go to my RNN here, after in the init, I'm just assigning all the weights and biases with some random weights, random numbers divided by 1000, so that it will be really close to 0. So weights will look something like this as well as the biases. Now after initializing, we just implemented feed forward layer. So it does the same. It will just take the weighted sum of all the weights as well as the inputs along with the hidden layer plus bias, and it will pass to the activation function, which is 10h, and then it will just calculate the output, because we have only one output, using the output weight as well as the output bias, and return it to us. So for example, let's say let's go to the RNN. Here we are just initializing our first hidden weights to 0, because initially, if we go to the diagram up, the first layer here, this only belongs to the input, right? It doesn't belong to any output of a hidden layer, right? So initially the output of a hidden layer we assign it to 0. So when it will be multiplied by the input in the formula, which is this, so this will be 0. So this whole term will become 0 and it will be negligible. It will be removed exactly, right? So the first layer, the formula will be input into input weight plus bias of hidden layer. So that is why we are initializing it with 0. For the first layer, it will just work like that, and after that, once we have the output of the first hidden layer, we are just updating it to the output of the last hidden layer. So we loop through all the inputs that we pass in our RNN, and we just calculate the hidden layer output for each input and keep on updating our hidden output. Since the RNN layer is depending on the last hidden layer output only, right? So we just need to update the same variable, and inputs we are getting in the loops, right? So using these two, we just keep on calculating the output of each hidden layer. After we get the output of last hidden layer, once the loop is over, we just use the same formula that we have here, which is this weights of hidden layer into the output of last hidden layer plus output bias, and we just return our output. So this is how we are training our, which we are just passing the input and processing it in the neural network. Here, this is some history we are keeping. So we are just keeping a track of output of all the hidden layers. This we will be using while we do the backpropagation feed. So in the backpropagation, we will need this to adjust our weights as well as biases. So that is why we are storing it. Otherwise, it's not needed. Okay. So this is our hidden layer. Let's try to demo it. Let me comment out this much part. So here I'm just creating a input vector for all these words which belongs to English language, and I'm just passing them to the feed forward layer of the RNN. And finally, we have a activation function at the output layer, and we just print the probabilities. So let's see how it will look. Let's clear this hole, and so as you can see, we got four outputs, right? Like a vector of four integers, right? 4-dimensional vector, where each entry represents the probability that probability of that sentence could belong to. So initially, if I print this as well, let me print the language index as well. So I just print this thing, print language to index, and let's run it again. So the 0 index represents our English language, first index represents the French, 2 German, and 3 Spanish. So as you can see, probabilities for each of them are almost similar, right? Close to, very close to 25. So we cannot say, our RNN right now cannot say what language this particular sentence belongs to. For that, we need to first train it. So let's start. How do we do that? Let me comment this out and open all this code. Now this is the backward phase, training. So if you have seen my previous video on training a basic neural network, you know we calculate the loss using some loss function. Then we find out how our weights or biases, change in weights and biases will change our loss. So if the change in weights and biases increases the loss, then we decrease the weight. Otherwise, we increase the weights or biases. Same thing we are going to do here. The only difference here is, in our previous neural network, the input was passed in the first layer, and first layer only, and the other hidden layers were depending on the output of previous hidden layers. Here input can be passed to other layers as well, right? So to calculate the loss, we are using a cross entropy loss function here, which is something like this. So this is PC is our output, and this is just the for example, if the output probability given by your neural network is 90%, then the loss will be something like this, which is 0.105. So let's represent some labels. So Y here represents the raw output from our RNN. Here P represents the final probability, which is after passing them to the function. Then C represents the true level of the certain text, which is the correct class. L represents the loss. These are the weights WSX, WSH, WHY, the input weight, the hidden layer weight, as well as the output layer weight. And we have two biases as well, hidden bias as well as the output layer bias. Now this is our loss. So after passing this to the softmax function, which gives us the final result of the output layer, we calculate loss like this. Now, as we know from our previous video, we find out the partial derivative on a particular weight or biases to calculate how the loss will change when the inputs will change, right? So we will do the same here. So we will first calculate delta L by delta Y for this function, which turns out to be something like this. If I does not belongs to the correct class, then the value is Pi, otherwise it's Pi minus 1. So for taking an example, let's say we have our probability something like this, and let's say we have a 3-dimensional vector in our output, and let's say our class is 0, which is having a probability of 0.2. So in case of other classes, the entries will remain same, but for this the loss will be pi minus 1, which will be minus 0.8. This is how we are calculating our loss here. Now we will do the same thing as we have done in the previous video, as delta L by delta WHY will be delta L by delta Y into delta Y into delta WHY, because again loss is depending on output Y is depending on the hidden layer weight. So this is how we are using the chain rule again to calculate the partial derivatives for each weight as well as the bias. So as we know, Y here is WHY into HN plus BY. HN is the output of the last hidden layer. So it's simple in this case, because while calculating delta Y by delta WHY, we know it will be HN. So the delta L by delta WHY will be delta L by delta Y into HN. Similarly, for delta Y by delta BY will be 1. So this will be the same. The delta L by delta BY will be delta L by delta Y. Now using these, we update our backpropagation function. We update our inputs and biases. After that, we just finally need to find our gradients on all the other weights and biases as well, right? So these were output weights and biases, so these were easy. But for hidden layers, weights and outputs, it also depends on the previous hidden layer output, right? So for example, Hn depends on Hn minus 1, then Hn minus depends on Hn minus 2, Hn minus depends to Hn minus 3, and so on, until unless we move back to the first hidden layer. So as the weight is same here and all the hidden layers, we cannot just derive it from the simple formula like we have done for the output layer, right? So here it will be delta L by delta Y into summation of delta Y by delta HT into delta HT by delta WXH. So while calculating for an input, we have to move back the whole all the layers of the RNN, right? Because X0 is being passed to H0, and then it is moving forward by hidden layer and finally going to the output. So we have to move back the whole time, right? Similarly for XNN, we have to move back for these two layers, right? So same with the WHH, we have to move back the whole layers because WHH is being passed in all the hidden layers, right? So changing that will affect all the hidden layers. So we have to take care of, we have to back propagate in time to do the very beginning to calculate how the hidden weights as well as the input weight should change. So that is what we are doing. We are taking the summation of all the hidden layers of delta by HT into delta HT by WXH, because changing a W input weight will affect all the hidden layers, which will affect Y and ultimately loss. In order to fully calculate the gradient of input weight, we will need to backpropagate to all the timestamps that we have known for backpropagation. So that is why we are storing these outputs of hidden layers here to calculate our delta for our input weight. So we are using it. For example, if I search for it in the backpropagation, so here how we are using it. We are just calculating our delta WHY here that we have seen in the above calculation. So let's move up. So our delta L by delta WHY will be something like this, right? So here we are just calculating the delta Y, and after delta Y we are just multiplying it, which is a vector as well, because delta Y is our vector, right? So as well as the output of the last hidden layer is a vector, right? So we are just taking the dot product of them. So we are just calculating them using like this. And similarly for delta L by delta BY, we are just simply stating as delta Y. Delta Y I am passing as a param in the backpropagation function. I am not doing the calculation here itself. So this is how we find out the loss of output layer weights as well as the output biases. And for the hidden weights as well as the hidden inputs, we are just iterating in a loop. So we are just initializing them 0 in the beginning, then we are iterating in a loop, and for each hidden layer we are just calculating the same thing. And finally, we just update our weights as well as biases based on the output we get from this code. So let's see how it looks like. So initially we have done this. Finally, we will just calculate this part and it will come out something like this. So our hidden layer is something like this, right? Input into input weight plus hidden layer, previous hidden layer output into hidden layer weight and bias. So the derivative of a 10h, if you know, will be something like this. For example, let's consider this whole function as a x. Then the derivative of 10h on x will be something like this: 1 minus 10h square x, right? So if we replace x with this whole formula whxt whst minus 1, it will be it is the formula for hidden layer output ht, right? So here if ht, this is the previous layer is ht minus 1, then the output of this layer will be treated as ht, right? So this is what we have replaced here. So 1 minus ht square into xt. So our final delta ht by delta bh will be similarly our delta ht by delta bh will be calculated by 1 minus ht square, because here we are calculating the bias, right? So our inputs and weights will be treated as constant. So here the variable is only 1. So if we calculate this partial derivative on bh by keeping all these constant, then the output will be 1, right? So this is why it is only 1 minus ht square. And in case of wxh, our derivative of this function will be xt, right? So this is the output is this terminology multiplied by xt. So we have just replaced here x with st, and then we have multiplied it with the partial derivative of delta ht by delta wxh. This is how we got this function. I hope we are clear on this. I will just explain it again. So when we are calculating the partial derivative of this ht on a input, we take the derivative of this whole function, right? So the output will be derivative of this whole function into derivative of this weighted sum which we are passing as an input in this whole function, right? So we know the derivative of this activation function is looking something like this, which we have here. Okay, because 10hx is this whole ht, right? So 10hx whole square is equal to ht square, which we have represented like this. Then we take the derivative of this internal equation, which is weighted sum. For wxh we get the output as xt, which is we are replacing here, and for bias we get the output of this partial derivative. For bias, the partial derivative of this input function is 1, which we are replacing here, and hence we are getting these two function for delta h by delta wxh and delta ht by delta bh. Now we are just calculating our delta y, how it is depending on that. So for until now we have how our hidden layer changes based on weights as well as the biases. We now just to propagate it to our output layer as well, right? So we are calculating dyt delta yt divided by delta ht. So according to the formula of this, it's just why, right? Now hidden state st also influences the future hidden states, right? So this we have got for output, this we have got for a hidden layer, for our input as well as biases. Now we have to calculate based on the hidden layer's output, right? Which will be something like this. So the delta y by delta st will be delta y by delta st plus 1 into delta st plus 1 divided by delta st. So it's the same chain rule, because we are calculating the partial derivative on this layer, which is dependent on the previous hidden layer. We apply the chain rule on the hidden layers itself. So it will be looking something like this. We already know how this looks like, so we just replace it here. So and at the end our formula will look something like this, which will be delta y by delta ht plus 1 into this formula. Okay, this is how we are calculating our loss, and we are updating our weights. So the same thing we are doing here in the mathematical terms. We are just taking the dot products for everything, because all of these are vectors. In case of in the previous video, in case of simple RNN, these were like values, right, as single numerical values. But here all these are vectors. That is why for every of them we are taking a dot product. After calculating how the loss will change on change of weights and biases, we just use the same formula, subtracting them using a learn rate and the value we have calculated, and subtracting it from the weights and biases. So if the derivation is positive, for example, let's say the value of it is something like 0.2, so increase in weights will increase in loss as well, right? So here, as we are subtracting, it will just decrease the weights. And if it is reverse, for example, if the value is negative, then increase in weights will decrease decrease the loss, right? So here we are subtracting, and the minus will both the minus will cancel each other out, and the weights will increase. The same thing we were doing in the simple neural network, right? Only the way we are uh, calculating our deltas is different. So let's see how it will look like. uh, so I'm just processing this data, I'm just passing it, and for each epoch I'm just printing the accuracy. So let me comment out this part, let's not do it for test. And let me run the script. So as you can see, these are the indexes for different languages. Initially the accuracy was really low, right? In the first epoch, after 20 epochs, then it started increasing, and later point of time it is like perfectly accurate. So after we train our neural network, let's see how the prediction goes. So let me comment out this part as well and run it again. So let's analyze it. So after we train our neural network, our final result is something like this. We have these indexes, and for this particular sentence, which actually belongs to German, the prediction is German. So if you will see, German belongs to index 2, and in this vector, the value at index 2 is the highest. So as you can see, all of them are pretty small, right? The value at index 2 is highest. Same for this sentence belongs to French, and the prediction is French because French belongs to the index 1, and in this the value at index 1 is the highest in all four of them. These are really small, right? 10 to the power minus 0.6, right? And here it is 10 to the power 0.1. So it's almost like 1 here, but here they are very, very small. So that is why the prediction is French. And same for others as well. English, French, and all the other test data, we are getting the accurate result. So if you want to check the loss in test data after each epoch, I can just show you that as well. So let me comment this out and run the script again. So now we are just getting the accuracy for each train and test data. Initially in our test, the accuracy was 0.250 because we were getting the same predictions for each language, right? As you saw previously in the video. Later point of time, it started increasing, and finally we got the highest probability that we can reach. So after that, it's same because the weights are not changing anymore. Okay, that is it for this video. I hope you liked it. Please like, share, and subscribe, and please comment if you want to know something about this, or if you want me to create any video on some topic. Thank you.